So welcome back to our second talk by the principal speaker. Lecture 2 will be on zippers, universal circles, and the unification of dynamical and geometric perspectives of three-manifold topology. Calegari.
Thanks very much. You know, some stuff that Jeremy talked about in his talk yesterday got me thinking and reminded me of a slightly different perspective on these Cannon-Thurston Peano curves that I was talking about at the end of my talk yesterday. And I thought I might just sort of briefly introduce it, only because there's a very axiomatic way of writing down what it is. And all the pieces emerge rather naturally from this axiomatic description. So just recall, the context is we're looking at these sort of Cannon-Thurston maps from circles to spheres. These are surjective. And there's a group acting on either side. This is a universal circle, and this is the sphere at infinity of hyperbolic space. But then you can sort of ask a kind of more general question: how would you recognize these kinds of sphere-filling maps without necessarily being given the group? So if I just gave you the circle mapping to the two-sphere, how would you somehow recover all this sort of structure? And the idea here, this is given by collapsing this pair of laminations, lambda plus or minus. Where would you sort of somehow see all this structure directly at the level of the map? And so there's sort of a rather nice axiomatic picture, which is maybe not the most general thing that you could write down, but it's general enough, and it certainly covers at least the case of surface bundles and a lot of other kind of interesting cases. And I thought I'd just sort of try to spell it out. So the idea is here, well, we just have, let's suppose we have a surjective map. Continuous. And we want the following to be true. We want, for, I'll just say, a dense set of closed intervals, I, proper closed intervals. Okay. Dense just meaning you can find the endpoints arbitrarily close to any two distinct points in the circle, and going around it in either direction. Right. So obviously, yeah. You could look then at, well, you could restrict F to the interval, and you've got a continuous map from the closed interval to S2, so the image is certainly going to be some nice, compact, locally connected set. And what you want is the axiom that, well, F of I should be topologically homeomorphic to a disk, and F of the boundary points should be homeomorphic to a pair of points S0 contained in the boundary of this disk. Okay? And really that's sort of the whole, all you need to sort of say. And then the idea is, well, here's your circle, and it's sort of mapping over to the two-sphere, and if I have an interval in here, which I guess I'm going to draw it in yellow, so it's going to come around like this, and the image is going to be topologically a closed disk, and the endpoints of the interval are going to pick out for you a pair of points in the boundary of this disk, and the rest of the disk, well, the rest of the boundary has sort of a red side and a blue side, and the pre-image of the red side in the interval is going to be a sort of a red counter set, and the preimage of the blue side in the circle is going to be a blue counter set. And each of these counter sets gives you a kind of lamination where the leaves are sort of the gaps. And just taking a union over this dense set of closed intervals gives you a dense set of the blue leaves and a dense set of the red leaves, and then you can recover this pair of laminations directly from this kind of construction. Anyway, so if you like sort of playing around with ideas, this is just something for you to mull about if you don't want to listen to the rest of the talk. Okay. Anyway, so this is just sort of a slightly different perspective on these kind of Cannon-Thurston maps here. And then, like, the point being that the consequence here is that this map can be approximated by embeddings. It's a sort of point of non-bumping in the closure of the space of embeddings. Everything is kind of canonical here in the sense that if there's a group acting here, which is equivariant with respect to this map, then the group sort of also preserves, or this structure preserves this pair of laminations, and so on and so forth. And the flip side is the Cannon-Thurston maps that arise at least from surface bundles over the circle, and I believe from other classes of universal circles, satisfy more or less this sort of axiomatic setup. There's maybe some slight kind of wrinkles that one has to put in there. There's a kind of annoying technical condition which is called the condition of having perfect fits, which complicates things slightly. I guess I'm probably going to talk about that in a second, so let's sort of move on to the next topic. All right. Yes.
So are you saying that if your surjective map from these circles satisfies this, then it comes from Cannon-Thurston?
Yeah. This is well, okay. Comes from a Cannon-Thurston map. I mean, there need not necessarily be a group acting here,
Okay.
but you can kind of recover the pair of laminations more or less canonically from this setup, so that if there were a group acting, you could recover the laminations that you construct here are group invariant and give you a way of sort of seeing that the circle is a limit of embeddings in a kind of canonical group invariant way. The point is it's a factorial construction. You can recover that. Okay. So yesterday we talked about surface bundles, and we sort of pointed out that if you have a surface bundle over a circle, it gives the universal cover a kind of nice product structure. And if we sort of furthermore chose a transverse vector field, then that product structure was sort of very clean. We have the universal cover structure of a product R2 times R in such a way that phi1 acted separately both on the R2 factor and on the R factor. So there's sort of two directions in which you might want to kind of generalize this. So here we have surface bundles over the circle, just say, with, so this gives us a sort of like foliation F. This is this foliation by surfaces with a transverse flow or vector field X, and this structure together gave us that X twiddle gives the universal cover, M twiddle the structure of a product R2 times R. I did that last time, in a way which is respected by the action of I1, and adapted on each factor kind of separately, with an action of I1 on this R2, which was the leaf space of this lifted flow, and we had an action of I1 on R, which was the leaf space of this lifted foliation. And so there's sort of there's multiple directions in which one might want to kind of generalize this setup. So surface bundle over circle is an example of a taut foliation. And this transverse flow is an example of a quasi-geodesic flow. And each structure separately, well, here we've got a universal circle. So we've got a universal circle S1U here from some compactification of this leaf space of the flow. But it was also at the same time, it was also canonically identified with the circles at infinity of the leaves of the foliations. There were two different interpretations. And so in either of these contexts separately, it turns out there's a construction of the universal circle where, in the case of the quasi-geodesic flows, again, there's a universal circle which comes from a compactification of the flow space of X twiddle. For the taut foliations, there's a universal circle which, well, it's now no longer kind of canonically identified with the circle infinity of the leaves of the pulled back foliation, but it has some relation to them. It has, let's say, well, I'm going to sort of say it in this way, a monotone relation. Relation to the circle infinity lambda for each lambda a leaf of this foliation. I haven't said what anything is yet, so let me sort of give some definitions. I'm going to start talking about quasi-geodesic flows. It's possible I might spend the whole hour just talking about quasi-geodesic flows, but if I don't, then I'll spend some of the remaining time talking about taut foliations. But actually, from the perspective of the zippers, it's the quasi-geodesic flows that are sort of a bit more important. But in any case, if you like taut foliations, you should know that there's a story with universal circles associated with that. So what's a quasi-geodesic flow? All right, so here, M3, closed, hyperbolic, X, a quasi-geodesic flow. What do I mean by that? It means that we pull back the flow lines to the universal cover. So it means that the flow lines of X twiddle, this is the pullback on the universal cover M twiddle, and because M is hyperbolic, this is identified with H3. These flow lines are quasi-geodesics. I guess I'm going to assume that everyone knows what is meant by a quasi-geodesic in a general metric space, but in particular, I especially going to assume that you know what is meant by a quasi-geodesic in hyperbolic 3 space. Okay? Bunch of different definitions. The parameterization is not really so important exactly. Like this is just, if you like, it's a vector field or it's a foliation. Different choices of parameterizations on a compact manifold are going to be by Lipschitz, comparable to each other. So any two different parameterizations downstairs will give you by Lipschitz equivalent parameterizations upstairs. So I don't really care about the parameterization so much. The key point is that these flow lines are all a bounded distance from honest bi-infinite GD6 in H3. Okay? So this is not exactly equivalent to, but certainly implies that each flow line is a bounded distance from an honest bi-infinite geodesic in H3. So the picture here is, well, the universal cover is H3, which is M twiddle, and we have this flow downstairs, and it lifts to a flow upstairs, And the flow lines upstairs are these, well, in particular, they're properly embedded lines in this B3, and they limit, in fact, to properly embedded closed intervals in the closed wall. So each flow line limits in positive time to some unique point in the sphere of infinity. It limits in negative time to some unique point in the sphere of infinity. And these 2 points for each flow line are different. Okay? So the idea is, so in particular, so we get, as a consequence, maps, well, I didn't say from what. So the space of flow lines, maybe I should have said this. Here's a fact. In this context, fact, the space of the leaf space of X twiddle, which I'm going to denote by P, is homeomorphic to the plane, so P for plane. And another fact, the endpoint maps are continuous, so E plus or minus continuous maps from P to the sphere at infinity. Okay. Not only are they continuous, well, this is the leaf space of a foliation on the universal cover, which was pulled back from a foliation downstairs. In particular, the deck group of the universal cover permutes the leaves, so it acts by homeomorphisms of the leaf space. So we get a nice action of pi1 here. We also have an action of pi1 here, and these 2 maps, E plus and minus, from the leaf space to the sphere at infinity, are intertwined, these 2 different actions. Okay? Yes?
What do you do to that long distance?
An honest bi-infinite geodesic in H3. Okay, yes. I guess I made a little bit of an effort yesterday to keep my handwriting only terrible. But yeah, I'll make more of an effort. Maybe if I just draw pictures and don't write words. Clearer. But anyway. So why are these sort of 2 things, why are these things true? Well, okay, so why is the leaf space a plane? And why are these sort of maps continuous? Both of these facts can be deduced from some implicit quantification that I've swept under the rug. When you talk about a quasigeodesic, you have to sort of quantify how quasigeodesic you are. Being quasigeodesic means that, well, there's sort of an additive constant and there's a multiplicative constant. If you have 2 points on the geodesic, then their distances along the geodesic compared to the distances in H3 are multiplicatively bounded up to an additive error. And you have to say what the multiplicative and additive errors are to say in what sense you're kind of a quasigeodesic. No matter what those constants are, a given global quasigeodesic will be a bounded distance from an honest geodesic. But here the condition is simply that each individual flow line upstairs is a quasigeodesic. And from that you want to deduce that there are uniform constants that work for all the flow lines simultaneously. And that's true. And the reason it's true is essentially just that being quasigeodesic in a hyperbolic space is a local property. Being quasigeodesic with certain constants is a local property. And if these things fail to uniformly be quasigeodesics, you could sort of extract a limit that wasn't a quasigeodesic. Okay, end of story. But in any case, there's sort of, what I should really say is uniform quasigeodesics, meaning implicitly there's some uniform bound in the constants, but you get that for free by the fact that M is closed. All right, but I'm not going to go into the details. Anyway, so this is true and this is true.
I have a question.
Yes?
So, do distinct flow lines have distinct pairs of endpoints?
No. All right.
You shook your head, yes.
Yes, that was space. And, you know, as I said, it's really hard to draw the plane without implicitly compactifying it by acting a circle, because how would you draw the extent of it? But I don't want to sort of assume more than I've kind of got here. Here is this plane. So the points of this plane correspond to flow lines in the universal curve. And I've got this map, these two maps, E plus and E minus, which both map to the sphere at infinity. And I don't want to say that the map is either injective or surjective, but what I can do is I can pick a point in the sphere at infinity, and I can ask, what is the preimage under, let's say, E plus? Okay? And the preimage under E plus is a closed subset of the plane, and it breaks up into a bunch of connected components. And here's the claim. Each of these connected components is unbounded. Here's a sort of fundamental observation, some fundamental fact. For all points P in, well, if it's not in the image of E plus, the statement is vacuous, so I might as well let it be in the image of E plus, and that's a capital P. The preimage E plus inverse of P, every component of the point preimage in P is unbounded. So it's sort of going to look like something like this. And the way I'm drawing it, I'm kind of drawing each of these preimages as something which is essentially tree-like. And the reason for that is the following. Well, supposing one of these point preimages, let's just suppose for the moment they were locally connected, so I think of sort of draw them as the way I've kind of drawn them here. Suppose one of them was not simply connected. So they had a complementary, say, let's say had a bounded complementary region, right? So suppose one of them had like a bounded complementary region. Well, let's look at a point in here and look at its image under E plus. That's going to be some other point Q. The point preimages of Q, the point preimage of Q under E plus is a union of components, and each component is unbounded. On the other hand, it's disjoint from the preimage of P. So you're going to have one component which is unbounded, but still somehow trapped inside this bounded region here. So that's obviously a contradiction. And the conclusion is that these components of the point preimages are simply connected and unbounded. And so you can think of them sort of as trees. So these components, and so in particular, I can define a set, E plus, which is the union of the set of ends of components of point preimages under E plus, and likewise, I can do the same with E minus. I get a collection of ends, and these collection of ends, each individually, are circularly ordered. So each of these guys individually are circularly ordered. Why are they circularly ordered? Well, the same reason that we talked about yesterday. They head off in the plane and they're disjoint. So if you have three of them, they head off in the plane and they're disjoint. Well, take a big compact disk and look at the last place, all three of them, first place, all three of them exit that disk, and they exit at three specific points on the boundary of the disk, and they get a circular order. It's compatible on four circles. Okay. And since none of this involved any choices, pi1 acts on this circularly ordered set, so by general nonsense, pi1 acts on a circle. You get one for each of these sets. But actually, I can make a single E, which is the union of E plus union E minus. And in fact, this guy here is also circularly ordered. And the reason for this is, well, a point pre-image, let's say E plus inverse of P, gives you these sort of disconnected pieces, these disjoint pieces. Each one has their ends heading out to infinity. The point pre-image of some other point Q, or even the same point for that matter, under E minus, gives you some other collection of sets. The pre-images under E minus and the pre-images under E plus might intersect, but now the intersection of the point pre-image of P under E plus and the point pre-image of Q under E minus is a compact set. So the reason is, so for all, let's say P, Q, and S2, E plus inverse of little p intersect E minus inverse of little q is compact. Why is that? Because this is the collection of flow lines that are asymptotic in forward time to P and are asymptotic in backward time to Q. And since all of the flow lines are quasi-geodesic, these flow lines are all a bounded distance from the geodesic, the infinite geodesic from Q to P. And since they are uniform quasi-geodesics, that bound is independent. In particular, they are all within a physically like a bounded neighborhood of that by infinite geodesic, so there's a compact family. Just pick a compact set. All of them have to intersect that guy. So there's a compact set which surjects onto the intersection here. And so what that means is, so if I have a component of the point pre-image of P, so this is in E plus inverse of P, and I have a component of the point pre-image of Q, the intersection is compact, and outside of that the ends are all disjoint, so they just come in some circular order. There it is. Just read it off. All right. So we get a circularly ordered set, and there's an action of pi 1 on it, and we can put this inside a circle and blow down gaps in a kind of canonical way, and we get therefore an action of pi 1 on a universal circle. Okay. Where do the laminations come from? Okay, so I'll just say for each component of a point pre-image, let's say of a point P, the collection of ends associated to this, I'll just say the ends of a component of this is a subset of this set E. And so we have, well, this E here is somehow, I'm going to say equals, it's not quite equals, but morally speaking, is a circle. So I get a subset of a circle, so here's my universal circle, and I get a collection of ends, and I get a collection of points in that. And what I do is, I just think of the circle as the boundary of the hyperbolic disk, and I think of this point, so infinity is a set of infinity. I take the convex hull in hyperbolic space, and I take the boundary of the convex hull, and that gives me a collection of leaves. Okay, so I just get a collection of leaves, and if I do that over any, all other kinds of subsets, I get maybe some subset things like this, who knows, whatever, and I get a collection of leaves like this. And the fact that the point pre-images, the components of point pre-images of different points under E plus are all disjoint from each other, says that the ends associated with different components are not linked in the circles, and therefore the chords in the disk that I get never intersect each other. Okay, so I just get a lamination like this. Okay, very good, you say, except what happens if each component has only one end? It's unbounded, so it has at least one end. But what if it has only one end? Well, if it only has one end, it's only going to pick out one point at infinity, and the convex hull of one point at infinity is just that point, and would get nothing. There would be no leaves there. That would be bad. So here's the problem. What if each component of each point per image has exactly one end? All right. Well, that would be a problem, but fortunately it doesn't happen. So why does it not happen? So here's the leaf space P, and here's the universal circle. So we've got the universal circle, here it is. Now it is true that, we've got R2 and we've got a circle, so we should be able to put them together and get a closed disk. And it is true you can do this, and it is true that there's a canonical way of doing it. And it is true that the pi1 acting on P extends to a continuous action by homeomorphisms on this closed disk, but I haven't yet proved it. But let's just suppose that I have proved it, okay? Suppose that each component had exactly one end. Well, what would that mean? It would mean that for each point in P, well, it's contained in some component, and that component has sort of exactly one end, and it heads out to some point in the boundary circle. So you get a map from P to the boundary circle. And if you worked a little bit harder, you could prove that this map was continuous. You would prove that it gave you a retraction of the closed disk onto the boundary circle, which you can't do. Therefore, it can't be the case that every component has exactly one end. Therefore, some components have more than one end, and therefore this collection of leaves is non-empty. So, solution, if every component had exactly one and we would get a retraction from this disk under its boundary, which is bounded. Okay. So I should say you can prove that this doesn't happen without actually proving that this circle compactifies this disk, this plane, but it does compactify it. So in fact, it's a theorem of my student Stephen Frankel. He proved that in fact P union S1U can be topologized. There's a natural way of topologizing it, which comes from this collection of ends. You can define some neighborhood open neighborhoods of points in this boundary circle. It's homeomorphic to a closed disk in such a way that pi1 on M acting here is continuous, is by homeomorphisms. All right.
So you mean it extends to this, the action set?
The action extends to the closed disk. Yeah. So without this, even without using this fact, we already get an action on the circle because I just constructed the circle directly as a set that the group acted on. But it's very convenient and pleasant that it does in fact compactify the plane with the pi1 action that came from the foliation on it. Not only that, but you can do the following thing. Let's build a copy of a two-sphere in such a way that the equator is S1U, and the northern hemisphere is a copy of the leaf space, and we'll give it a plus to indicate the northern hemisphere, and the southern hemisphere is another copy of the leaf space, and we'll call it P minus. Well, there's a map, P plus, on the top, and there's a map, E minus, on the bottom, which are continuous maps to this sphere infinity of hyperbolic space. And of course, there's still I1m here, I1m here. So this is maybe part 1 of Frankel's theorem. Part 2 of Frankel's theorem, they're really two different theorems, but he proved them both, so I'm going to make it one theorem with two cuts. These two maps here, the endpoint map, the positive endpoint map on the top thing, and the negative endpoint map on the bottom side, they actually can be, they both limit to continuous maps from this universal circle to S to infinity, and even better, they limit to the same continuous map from this circle to the sphere of infinity. So they agree, and you get a map E, which is defined on the entire sphere, which is just E plus on the top hemisphere. It's E minus on the bottom hemisphere. And it's the limit of both of these on this boundary circle. And fortunately, those limits agree. Define a nice continuous map E. So you get a surjective map from this S2 together with this pi1 action to this S2 together with this pi1 action. And so you can just take the point pre-images, and that gives you a decomposition here. And the decomposition here is basically unions of pieces of this kind glued together along the boundary. So it might be the case that you have one of these sort of red pieces up the top, which limits to a bunch of stuff down here. And it might be the case that you have some blue guy on the other side, which also happens to have an end in common that happens to agree with this end. We have to worry a little bit about this. The set of ends here, the ends of the blue guys and the ends of the red guys were all disjoint. But once you put things in the circle and take closures and blow down gaps, things might get identified. And they can. So this phenomenon is sometimes called a perfect fit. Well, it's always called a perfect fit, in fact. So I'll just say perfect fit. A perfect fit is when one of the leaves of, say, the red lamination and one of the leaves of the blue lamination have an endpoint in common. It can happen. And by the way, this might be sort of a leaf which is a limit of leaves here. When we took this lamination, we had to take a closure. So not every leaf necessarily was associated directly to it. But in any case, it could happen that there are some of these perfect fits. Nevertheless, the point pre-images are whatever they are. They do define a decomposition, and you get a nice Cannon-Thurston map. Well, in fact, this is the Cannon-Thurston map. So E here is a Cannon-Thurston map. So E, we just restrict it from S1, this thing here, it's pi1 equivariant, and it's obtained by quotienting out the relation generated by the laminations lambda plus and lambda minus. The equivalence classes are now no longer literally the leaves, because you might have one leaf that's glued to another leaf, which might be glued to a third leaf, and so on and so forth. Fortunately, this process terminates. But it is what it is, and you get this sphere filling Cannon-Thurston. All right. I've got a little bit of time left over. So I wanted to sort of say something about the relationship of this picture to the zippers. So one case which is particularly nice here's a special case. Is the case where you have no perfect fits. So quasi-geodesic flow with no perfect fits. So what does that mean? It would mean that the red lamination and the blue lamination, no leaf on the red side and the leaf on the blue side have a point in common. And in that case, the actual point pre-images are just, well, the leaves and the kind of the components of the things, the complements that they have. So the actual decomposition elements are very simple in that case. So in this case, Well, it's still true that E of S1U is all of S to infinity. That's obviously true. And the reason is, well, whatever the image is, it's pi1 invariant, and it's also closed, and it's also non-empty. And it's a basic fact that the action of pi1 on the sphere at infinity, if M is a closed hyperbolic 3 manifold, this action is minimal, meaning that any closed, non-empty pi1 invariant set is the entire sphere. And since the image of this circle is closed and non-empty in pi1 invariant, it is the entire sphere. However, you could look at E restricted to P plus, and you could look at E restricted to P minus. These images are not necessarily closed. They are pi1 invariant. They're path connected because these are path connected and this is continuous. This Z plus, or this Z minus. If there are no perfect fits, then Z plus and Z minus are disjunct. Because there's no point on the top side to get us identified with a point on the bottom side. Because if it were, you'd have to have a leaf that was at a common endpoint, glued one to the other. These are disjoint. They're path connected because they're the images of path connected things under continuous maps. And they're pi1 invariant because, well, pi1 acted everywhere, and this is just completely functorial construction. In particular, these are zipper. This is an example of a zipper. So, conjecture. All zippers arise this way, meaning anytime you have a zipper, there is in fact a quasi-geodesic flow without perfect fits, which gives rise to it. I think this is quite likely true. Yes?
You state what perfect fit is in terms of,
In this context, you have a circle, and you have a pair of invariant laminations, lambda plus and lambda minus. And probably it's true that these are the only invariant laminations, meaning that if you have any chord at all whose translates don't cross itself, the union of the closures is one of them or the other. So probably you can recover it just directly from the dynamics. No perfect fits means no red leaf and is there any point in common with a blue. Yeah. All right, special case. Special case of the special case. I guess it's somewhere for that as an example. Suppose M fibers over the circle. Let's let F be the foliation by fibers. Let's let X be any vector field, one-dimensional foliation transverse this foliation by fibers. Then, 1, X is quasi-geodesic. And 2, there are no perfect fits. Let's prove this. So we've got our three-manifold, which fibers over the circle is the map to the circle. The fibers are basically the point pre-images. And we've got a vector field which is transverse. So there's a one form on the circle, which is, I guess we'd call it d theta. It's not really d of anything, but we would call it d theta, which is, we integrate it around the circle, we get 2 pi. We pull it back, I guess I'll pull this pullback of it, maybe call that alpha, that's a closed, non-degenerate one form on our 3 manifold, whose kernel is tangent to the surfaces. And so in particular, so alpha is closed, non-degenerate one form, and on the other hand, alpha in a product with our vector field X is everywhere positive, and since we're on a closed manifold, that means the minimum is positive and the maximum is positive. And so, if we lift to the universal cover, and we take a flow line of X twiddle, and we integrate, well, the pullback of alpha, I guess. I'm going to call alpha twiddle is just the one form on H3 obtained by pulling back the one form alpha on M under the universal covering map. Yeah. We integrate this guy here along any segment I contained in X twiddle. This is less than or equal to and greater than or equal to, I guess, just the length of I times a constant 1 and the length of I times a constant 2, right? Because just the norm of alpha is bounded both below and above by positive numbers. In particular, the length of I is comparable to, well, the norm of this one form is bounded. And so if you had any other geodesic segment, it's closed. So the integral of, we had like maybe some geodesic gamma sub I with the same endpoints as this subinterval I, the integral of this one form over gamma I would be the same as the integral of this one form over I. But the integral of this one form over gamma I is bounded by the length of gamma I times a constant, namely the norm of alpha. In particular, the length of I is comparable to the length of gamma I. Right, this is not meant to be a hard theorem. It's a very easy argument to imply that the flow lines here are quasi-geodesic. Really nothing to do with hyperbolic manifolds at all. But the conclusion, once you know the flow lines are quasi-geodesic, that they're a bounded distance from honest geodesics, that's where we use hyperbolic geometry. Not only that, but I claim that the endpoint maps, E plus and E minus, have disjoint image. So why is this true? So E plus intersect E minus is empty. So why is that? Well, what am I saying? I'm saying that there can't be two separate flow lines which, so to speak, limit to the same point at infinity, one in positive time and one in negative time. And the reason should be kind of obvious, because basically, we pick some point in the interior and go to some point on this flow line and go to some point on this flow line, and we integrate alpha twiddle along that. Well, it goes to whatever it is. And then we integrate alpha twiddle along the green flow line, and it increases to positive infinity. On the other hand, if we go here, we integrate it along this guy, it goes to negative infinity. Since it's a closed one form, and these two things are a bounded distance apart, the integrals of the one form over them should be comparable. The difference between them diverges, so they're not. So that's true. Therefore, conclusion. In this case, E plus or minus E are a zipper. So this is a, I don't want to call it cheap, but this is a very, very easy way to construct zippers, and you can, so obvious that they really wanted an example. This is, I mentioned this example, but this is an example. Notice the power of this technique. So here's a strategy to construct zippers. So we wanted to boil this down. A strategy to construct zippers. We want some space, P. It's going to be a space of, let's say, quasi-geodesics in twiddle, or space or family of quasigedesics in M twiddle with the following property, that we want it to be pi1 invariant. We want there to be there should be some by Lipschitz function, by Lipschitz, is that what I mean? Some uniformly Lipschitz function I don't want to call it theta from M twiddle to R, which goes to plus infinity or minus infinity on the elements of P. So these are supposed to be oriented quasigeodesics, and if you go along one of them in the positive direction, theta should go to positive infinity, and if you go along it in the negative direction, theta should go to negative infinity. And because these are going to be uniformly Lipschitz, what that means is that the positive endpoints of P and the negative endpoints of P will be disjoint. So you're going to get two disjoint pi1 invariant subsets of the sphere at infinity, the positive endpoints and the negative endpoints, and you need one further condition, which is that P plus or minus of P are path connected. Well, if this family P was path connected, then its image is going to be path connected. Okay? P doesn't necessarily need to be path connected for its image to be path connected, and tomorrow I'll give some examples. But notice here, in the case of quasigeodesic flows, I had a very specific family of quasigeodesics, namely the flow lines, and they were all disjoint from each other, and they were very kind of, leaf space was a plane, and we really used the topology of the plane and separation properties and disjointness and everything else to cook up the universal circle. Here, all we have is just a completely arbitrary family of quasigeodesics, which is pi1 invariant, whose endpoints in positive and negative direction are disjoint, and with some kind of path connectivity. So there's enough of them that the images are path connected. This gives a zipper. And the theorem that I think Inu will talk about Inu will talk about tomorrow, is that a zipper gives rise to a universal circle and a pair of laminations. So just this data alone, we get somehow magically a universal circle and a pair of laminations. Where's the leaf space? Where's the plane? There's no plane. We just get a circle somehow by magic. We get a pair of laminations by magic. So this is sort of the power of the perspective of the zippers. You get the universal circle, you get the pair of laminations by working with the dynamics of pi1 and the sphere at infinity, rather than working with the dynamics of pi1 on some complicated topological space associated to the dynamical system that you care about. Well, this is a little bit vacuous without some examples, but tomorrow I'll give some examples. So two contexts in which you can find such families arise from quasimorphisms, certain kinds of quasimorphisms on the fundamental group, those so-called uniform quasimorphisms, and certain kinds of left orders on the fundamental group, so-called uniform left orders. So those two algebraic structures on the fundamental group of hyperbolic and three-manifold give rise to families of quasigeodesics with this sort of property, thereby they give rise to zippers, thereby they give rise to universal circles. Okay. So that's tomorrow, and I'm going to stop now because I think it's been about an hour.
Questions?
Yes.
Is there a characterization of all the symbols that we get?
Sorry, can you?
Is there a characterization of all the different symbols we can get? Is there a space of symbols?
I don't know. I think that's a very good question. At the moment, what we have is a definition, some constructions, and some corollaries of the structure. It seems to me interesting enough that it's a well-motivated question to ask what are the possible descriptors that you can have. By the way, here's a question which probably has a simple answer no, but can you find, given M a hyperbolic closed hyperbolic 3 manifold, can you find 3 disjoint path-connected pi-1 invariant non-empty subsets of the sphere of infinity? I think finding 2 is, I think it's surprising that they do exist, but we just saw some very explicit constructions. Not only do they exist, they're all over the place. But can you find 3 disjoint ones? I conjecture not, but I don't know why. Maybe. Have to look pretty weird if you could. But in any case, that's sort of a marker post for my ignorance, if you like. Other questions? Fran?
Yeah, I was wondering if you could repeat why you have no perfect fits.
So, I stated, maybe without proof, but when there are no perfect fits, the images are disjoint. And the converse is also true. Because if you had a perfect fit, well, you'd have stuff on one side and stuff on the other that land at the same point in the circle, and their images in the sphere of infinity of E plus and E minus would be the same point.
So, why are the images disjoint?
So it's the converse of that. If there are none, I mean, because you could say what the point preimages are. If there are no perfect fits, the point preimages are basically the decomposition elements, which are exactly the red leaves and the blue leaves, and the complementary regions to those. And those are disjoint, so the point preimages are disjoint. So the images are disjoint. Yes?
So this zipper construction, how close is it to unifying this concept of universal circles? Say that also comes from, say, taut foliations and other perspectives.
Yeah, what I would say is that I think that zippers is the right perspective to unify the theory of universal circles without perfect fits. For universal circles with perfect fits, we have a sort of a very tentative, conjectural sort of object called a p-zipper, where now z minus and z plus can bump, but they can't cross. It's a little bit more subtle, it's slightly harder to work with. I believe in that case you should still get a universal circle and pair of laminations now with perfect fits. The whole theory is more complicated, but I think that that context should exist. But for the moment, the zippers should be just sort of the universal object that corresponds to universal circles without perfect fits, whatever that means. And maybe you could, as I say, maybe you could just sort of say something axiomatically. This discussion that I gave you at the start of the lecture, given a map from a circle to a sphere satisfying this very kind of concrete axiom, you get a pair of laminations in a universal circle. If you get a pair of laminations of the circle, it's completely functorial. If there's a group acting, it's a universal circle. It should be possible to find the zippers in that picture. So I feel like that's the kind of, there's a sort of a universal back and